Can you hear me now? Okay. So we have some problem. Oh, now it's working. Okay. Okay, so now it's obviously working. So let me just briefly repeat. So I just was talking about the exam conditions. So you are allowed to use 2 pages A4, front and back. So at the end you have four pages basically, where you can write down the important formulas. And yes, you are not allowed to use calculators or electrolysis, and you will also not be. They won't help you. Okay, do you have questions related to the examination conditions? Yes, so here's the question if all short formulas can be written on these 2 pages. And well, on the 2 pages you can write whatever you want. You can write formulas, you can write examples from the lecture. Maybe this would help. For example, in my tasks, you will find even tasks where you will need to come up with some Tanner diagrams. So maybe it would be smart to also write an example with a Tanner diagram on your formula sheets. So this is okay. Okay. As we are already speaking about the exams, I already mentioned the Tanner diagrams will be important, so you should be able to come up with Tanner diagrams if I give you like a parity check matrix, but this is not really difficult. Then you should look again at task what we did at the beginning, like this syndrome decoding. You should be able to come up like with a syndrome table for a given code. This should be possible. What else do we have? One task where I asked for log likelihood ratios. So also look again on the definition of this log likelihood ratios where we derived this stuff. But it's an easier example, so you don't have to deal with Gaussian distributions. So I made it easier. And what else do we have to do? These 2 guys. Also look at the example like what we did last time. The parity check matrix of the 802.11n standard, how this was defined with this base matrix, which gets expanded to a larger matrix. Also look at this, how this was working. This might help you in the exam. But let me also remind you, first part of the exam is Dr. Wolf's material, and typically the students have more difficulties solving his tasks. So don't forget the things Mike Wolf taught you. Have a look at what he did and so on his examples. Okay. So any more questions related to the exam? Okay, so as I said, for the students in Russia on Monday will be the date of the exam. So the students here in Ilmenau have some more time. Yes, so there's a question related to the sample exam. So I uploaded one, actually you find. Here, the sample exam. Well, you will see this is not so much related to what we actually did this year. So, well, of course, you have here some binary erasure channel. This is more Mike Wolf stuff. Let's explain in your own words. This year, I don't have something like this. So we didn't talk about the convolutional code so far. We will do this at the end of the semester. So this is not relevant for the exam, at least not for the Russian students. We'll have to see how far we get there in the last 2 weeks of the semester. I think we can still complete also the convolutional codes. But as I told you before, I restructured the material a bit because the convolutional codes, actually many students know it from their bachelor studies, the basic block codes and convolutional codes. And nowadays the LDPC codes and the polar codes are used. This is why I treated those ones before. So for the Russian students, at least, you will not find a task on convolutional codes in the exam, and also not the recursive codes, the UMTS turbo codes. As I said, they have been replaced by the LDPC codes. So also this is not so much of importance anymore. Yes, and basically the tasks related to the LDPC codes and the Polar codes are new. So that's why we don't have a sample exam so far. This is new for this semester that we treated this in so much detail. Okay, but as I said, look at the examples that we solved in class, and they are quite related to what you will see in the exam. So here's also a question in the chat. Please some more calculations or theory. Okay, so it's a question related to the exam. If you have to do more calculation or if it's more theory, well, you just look at example, starting with last time. Actually, we start here. It's always a question, do you consider something as calculation or as theory? So just for example, imagine I ask something like this. Of course, I would select a matrix which is not as big as this one. I would select a matrix which is still big enough that you can enter all elements in the matrix. So I would, for example, come up with a task where you have here some numbers. The submatrices might be of size 3 by 3. And then basically I ask you to construct parity check matrix and the Tanner graph. So this would be straightforward. So you need to know how to deal with this cyclically shifted identity matrices here, how to construct such a matrix if you have a so-called base graph or base matrix available, and actually also the meaning of this matrix. The next useful question would be come up with the equations how to calculate the parity bits from the parity check matrix. These are like logical questions. Can you deal with parity check matrix which is given in such a form as we will find it in wireless LAN or 5G? And do you know about the meaning of the parity check matrix? So how can we use the parity check matrix to calculate the parity bits? How to do the encoding? We only know check matrix. Also there, we had some examples in the lecture. Okay, and now it's just a question, do you consider this as calculation question or theory question? Well, I would not really hardly distinguish them. It's just a question to see you understood what we treated here and you know how to apply what we learned. This will be the goal. Okay. So let me see. We will start again by explaining what we did last time. And as I already said, this will be relevant for the exam. So we started with again, an example for the LDPC codes, a practical example, so from wireless LAN. One of the 12 possible coding schemes and block length that could be used in LDPC codes for wireless LAN. Here we selected the RAID 3/4 code, which has a block length of 1944 bits, out of which 1458 are nation bits. So this actually results in this code rate 2/4. And we have a minimum Hamming distance of 12 for this code. So already quite a powerful code. And it's defined similar as in our example related to the 5G standard. Actually, it's a bit easier as in 5G because we don't have this high flexibility that we actually have in 5G. So we are restricted here to certain combinations of code rates and block length, whereas in 5G we are like fully flexible. But here we selected this example, and the parity check matrix is again defined by such a base matrix or base array or base graph, however you want to call it, containing some numbers, where the numbers basically indicate the shift of an identity matrix. Here in this example, we have blocks of size 81 by 81. So a number of 48 here means we have the identity matrix shifted 48 times to the right. So this will result in a matrix with such a structure. And at the end, to generate our parity check matrix, we need to replace this 48 here by a matrix here of size 81 by 81, cyclically shifted identity matrix. So this will go in here. Shifted by 29 will go in here, 28 here, and so on. We also have blank spaces here in this definition of the wireless LAN LDPC codes. Blank spaces just mean we have a zero matrix of size 81 by 81, which goes in here. So here I also have a comment on the zero matrices. So they are sometimes described differently. Here they are just left blank in the definition of this array. In 5G, they will be denoted by a -1 in this matrix. Yeah, well, because 0 and 1 we cannot use. 0 is the identity matrix shifted by 0. So that's the identity matrix. We cannot use this one. 1 is the identity matrix shifted by 1. We cannot use this one. So in 5G, a -1 is used for the 0 blocks going in here. Or sometimes you also find like an infinity symbol. So if you have an entry here of infinity, this would also mean we want an all zero matrix to go in. So this is different, the standard that you are, but the principle is always the same. 0 blocks in this matrix, or we have cyclically shifted identity matrices that go in. Okay. Then we have the first part of this parity check matrix. This is related to the information bits. And we have the second part, which basically belongs to the parity bits. And from this, we can actually determine the parity bits. Maybe we should do one more example on this one, but I think we also did this already. Look at an example where we had a more simple parity check matrix, maybe like 7,4 Hamming code, and look how you can determine parity check bits just from knowing the parity check matrix. So this would be also one recommendation. Try to look at this example again and think about how to determine parity bits looking at the check matrix. So how to calculate them from the bits, use 0 to, in this case, 1,004. Okay. So then we had an example where I've shown you that, of course, it somehow makes sense to think about how these numbers here could be chosen in a good way, or what would be bad way to choose these numbers. And of course, we have seen that these numbers are related to how this parity check matrix looks like. We have here the identity matrices put in here, shifted by 4. Then one more shifted by 0. Here another one shifted by 0 and another one shifted by 4. And we have seen if we select our base graph like this, this wouldn't be very smart, because we will see right from the structure in this parity check matrix that we will get 4 cycles in the Tanner graph. So this means it would be not very smart to choose numbers in a base graph like this. as we would get 4 cycles, actually many 4 cycles. Here another one. Really get many 4 cycles. This would be like the worst case how I could select entries in this space graph. So we could come up with some design criteria how to select those numbers in the base graph in a smart way. We didn't really go deeper there. This would take some more time, and we would have to go even more into detail on this cyclically shifted matrices that generate this parity check matrix. But what we should know already is that it would be smarter, for example, to select base graph like this, where we have a 5. Just imagine you shift this first matrix one step further. If we shifted this one step further, what does this mean? Should have so this would basically correspond to the shift by 5. And notice already, if I shift the first identity matrix by 5 instead of 4, I will break up all these 4 cycles. I have a way better bit error rate performance if I selected here a 5 in this graph. And this is basically how we could come up with a design method, how to find a good base graphs. So one approach could be to select these numbers randomly in a first step, but in this case, still such combinations could occur. Then I would introduce a second step to verify if my random matrix will result in some 4 cycles. And then I would remove the 4 cycles by changing some of the numbers. So there's actually one simple method how to detect these 4 cycles. So I was reading a bit about this yesterday. So for example, if you take always the sum of 2 rows of this matrix. So take this row, first row, and this row, 4 cycle. If you sum the elements of these 2 rows, get here 0, 0, 0. Here you will get 2, 0, 0, 0, another 2, and some more zeros. Or if you had a 1 here and a 0 here, you will get 1. So if you sum 2 rows, and in the resulting vector, you will observe 2 times a value of 2, then you are sure you will have a 4 cycle. It's 2 rows. Could think about this. If I sum the first row and the second row, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So no entry of 2 if I sum the first 2 rows. So from this I can conclude in the first 2 rows there cannot be a 4 cycle. This would be a simple method to verify if a parity check matrix has 4 cycles or not. I just need to build sums over all combinations of rows and check for the numbers of 2 that are contained in these sums. This would be a simple approach to detect 4 cycles in a matrix. So in the paper that I was reading related to this, they also did this for the 6 cycles. So if you sum any 3 rows of our parity check matrix, and you will find 3 times a 2, the resulting vector, you can conclude that you will have a 6 cycle. But of course, this also is somehow tedious. Just imagine you have a matrix like with 1000 rows, and you will want to calculate sums of any combinations of 3 rows. This will be quite some effort to use. But at the end, it's a brute force method to detect if you have 6 cycles in this matrix or not. So there are several methods how you could detect these 4 or 6 cycles in a matrix, and then it's straightforward how to modify entries in the matrix to get rid of these 4 or 6 cycles. Okay, so this just as information, and here one graph where we basically see how the bit error rate performance is limited if you have 4 or 6 cycles. So typically the design goal is to avoid the 4 or 6 cycles. Okay, and then we basically started with the polar codes. So this is the second class of codes that are used in 5G. And with the polar codes, we try to polarize the channel. Actually see this today. We already started there last by introducing this channel model. So we use a simplified channel model here. We just think about the binary symmetric erasure channel. But of course, this could also be done by using an additive white Gaussian noise channel. It will just be more difficult then, as we need to use again log likelihood ratios to do our steps. So for the understanding point of view, it's easier to start with this binary symmetric erasure channel to understand what is going on with these polar codes, what is the benefit and principle. Okay, so we started by introducing this channel model using W, this binary symmetric erasure channel. We can have channel inputs x0, channel outputs y0, and we can have correct transmissions with probability 1 minus p, or uncertain transmissions, wrong transmissions with probability p. So this is how our channel model is defined. And we basically started by looking at, let's say, 2 subsequent channels. So you could imagine this channel at different bit intervals. So we transmit the first bit over the channel, transmit the second bit over the same channel, assuming that the channel doesn't change within this block size, for example. So if we do it like this, this would just mean first time step we transmit U0 over this channel, second time step, here if I do it this way, I transmit the same bit channel. So this would basically be just model partition code. Then we basically extended this example by the basic idea of these polar codes. We introduced this precoding network channels. So where we basically say we input 2 bits in our system, and we basically use this precoding function where we say the first bit that we would like to transmit over our channel should be the sum of both input bits. The second bit that we transmit over our channel should be just the same as our second bit to be transmitted. So precoding, first guy is the sum of both, the second guy is just the second bit. This is what we transmit. At the receiver, we observe the values y0 and y1, and again, referring to our channel model, we could have the correct transmission here. So this means if no error occurs, probability 1 minus p, what we observe here at the output will be the same as what we have at the input. If things go wrong, with probability p, we will observe the question mark here, so the erasure symbol, no matter what we transmit here. So it could be we transmit a 1 here, we have the erasure event with probability p, we will get the erasure symbol at that. Okay. So then basically we started with the first task. We want to decode bit U0 from our observations y0 and y1. So this is why I wrote down here the combination y0 and y1. So what values can occur here for y0 and y1. So the first case that we have to consider is if we have the correct transmission on both channels. This will happen with probability 1 minus p times 1 minus p times the correct transmission. And no error on the first channel means y0 will be just the sum of u0 and u1. No error on the second channel, so this means my observation y1 will be just the same value as u1. See, u1 becoming here x1, no error on the channel, becoming y1. So we get the correct observation here at this second output. So as I said, we know the probability that this will happen, correct transmission on both channels. So then, considering all cases that can occur, for example, the erasure event on the first channel, so with probability p, things go wrong during this transmission. So this means we observe the question mark, the erasure symbol here, the first output. No error on the second channel, so we observe U1 correctly here at the second output. So in this case, we just know U1, and this will happen with probability p times 1 minus p. Next one, correct transmission over the first channel, erroneous transmission over the second channel. So we will get a question mark symbol here, and we will observe the sum of both bits here at the first output. And well, of course, the worst case, errors on both channels. So we will observe twice the erasure symbol here. Of course, in this case, we have no chance to estimate our transmitted bits. We know nothing. So those are the 4 combinations that can occur at our 2 channels. And then we basically thought about in which case is it possible to actually detect or estimate U0 from our observations y0 and y1. So notice, just in the first case, it will be possible. So if I know U1, and if I know the sum of U0 and U1, I can determine U0. For example, if the sum will be 0, observe there, and U1 is 1, then basically I just need to ask the question, so what value U0 plus value U1, which is 1, results in a 0, and from this I can conclude U0 must be 1. So in the first case, I could basically conclude on the value of 0. In the second case, I'm lost if I only know U1 and I don't know y0, x0, so there's no way I could come up with an estimate for U0. So here, no chance to get U0. Also here, from just observing the sum of U0 and U1 correctly, without knowing U1, also here, there's no chance to determine U0, because I don't know the value of the second bit. And also in the last case, as already said, no chance to determine U0. So from this, we can basically conclude that just looking at this example, only in the first case, it's possible to decode it correctly with probability 1 minus p. So this means we can also model this first decoding step, or this first odds that we have here, as a new channel, W minus, also as a binary symmetric erasure channel where things go wrong with probability 1 minus p squared. So this is again the probability that we can get U0 correctly. So 1 minus this probability will be the probability that things go wrong. So we basically model this first decoding or this first transmission step as a new channel where we have the outputs y0 and y1. And from those, we try to estimate u0. And with probability 1 minus p squared, this will be possible. And 1 minus this probability will not be possible. We use a number as example p being 0.1, 10% error probability. We see that this already turns out to be 0.19. So this will be a higher error probability when trying to 0. Because so far this is bad, we want to improve. But this we will see now in the next step, basically, when we talk about next step where we want to decode u0. And there we will basically use the fact that we now already have an estimate of u0. So we code u1 by using y1, y0, and u1. Some more information available now, which will result in a better decoding second bit. Yes, so here's the question, why we use this term artificial channel. Later on, it will become more clear. So the physical channel that I treat here is really this binary symmetric erasure channel. You will see that when we talk about these artificial channels, I basically include this pre-coding network channel. So then it's not only the physical channel, but it's like the physical channel plus the pre-coding network. And this is what I call then the artificial channel. My bit to be transmitted will also face the input of this artificial channel, but inside this artificial channel, it will go through the pre-coding network and then over the physical channel. It's just basically moving some more stuff in our channel model. Exactly, yes. Here again, the statement from a student. So the physical channel, including the pre-coding network, composes the artificial channel. Yes, exactly. We will see this more nicely when we also have the second channel, the good one. Then I will directly draw it again, physical channel and artificial channel. It will become more. Okay, so the next step. Estimate on the observations zero estimate zero. Besides, we could also use here u0. It's actually, we don't know u0 100% safe. We just have an estimate of u0. I will comment on this later on. So let us draw our network, a recoding network. Variables that we know 0, 0, 0, u1, X1, Y1, our physical channels W here. Now we want to use these guys to this one. So, and I will do it in the same way as we did it before. I want to think about now the values y0, y1, 0. Because we will get again like 4 combinations. Again, errors could occur on physical channels or not. So let's see. Let's start again with the first case, assuming no error. No errors on both channels. So what will be y0 if no error occurs? Y0 will be u0 plus u1. Let me also use some color again to illustrate this for you. So this goes up here, this goes here. So what will be y1? So y1 be just u1, so this just goes here. And u0, well, we just know this from our observation. So right here, like known. Again, this is the case, no errors will happen with probability 1 minus p on the first channel and probability 1 minus p on the second channel. So with probability one minus p squared. Again, thinking about the cases, assume an error erasure event on the first channel. So our observation of y0 question mark. Assume correct transmission on the second channel. So this means our observation y1 will be the same as u1. And well, u0, we know it from before. 0. So next one, with probability. Yeah, 1 times the error event or erasure event, 1 times correct transmission will result in the probability p times 1 minus p. Let's have a question from the chat. If the plus is a modulo 2 sum, yes, the plus is a modulo 2 sum. Yeah, only thinking in binary space here. Okay. So next, error on the second channel. So let's see, somebody wants to comment. Akash, feel free to comment. Is this working?
No, sir. It was accidentally happened.
Ah, okay. But anyhow, it's nice. I discovered a new function here.
Even me too.
Okay. Okay. So the third case, correct transmission over the first channel, wrong transmission over the second channel. This means at the first output, we observe the sum of both guys, U0 plus U1. We have the erasure event on the second channel. So here we observe the erasure symbol, and we know U0 from before. Also, this will happen with probability, yeah. So write it there. Same probability as before. And at last, the worst case, errors on both channels. So we observe the question mark for Y0, observe the erasure symbol for Y1, and we know U0 from. This will happen with probability p square. Now think about the cases in which we can conclude on the value of U1. So this is what we want to determine now from our observations. Think about it. Well, obviously the first two, we directly have a correct observation of Y1. This is easy. There we know of U1. So there we know U1. What about the third one here? We observe the sum U0 plus U1 correctly, and we know U0 from before. Also there we can conclude on the value. So in the first three cases we can determine U1 correctly. In the fourth case, we only know U0 and nothing else. So in the fourth case, there's no way we can. So let's state this here. In the first three cases, one can be determined correctly. Just in the fourth case, error with probability. Yeah, p square. Yes. Ah, okay. So here's the question again about the fourth case, why we cannot tell something about U1 in this case. So just imagine we have the erasure symbol here that we observe. We have the erasure symbol here. So this means we don't know x0 and we don't know x1. This could be anything if we observe the erasure symbol here. And we know U0. So I know what is going in here, U0, but I don't know x0. So then I cannot answer the question. So what needs to be summed with U0 for an unknown output? I cannot answer this. If I had x0 here, I can say what needs to be summed to U0 that the sum will turn out to be x0, like 1 or 0. Then I could tell. But if I don't know the outcome of the sum, there's no way to tell the value of U1. Yes, yes. So if you only know one element in your sum and you don't know the outcome of the sum, there's no way to determine the other element. Okay, so we will model this. As binary symmetric erasure channel with erasure probability square. So we call this the W minus channel, W plus. So then let me summarize this, because those were basically the main steps that we need to understand how this is working. Get from this two simple W channels, from the physical channels, to our two artificial channels, W plus and W minus, the good one and the bad one. So for example, if we use again P of 0.1, then P square will be already 0.01. This action will be quite safe, very low error. This is why we use the term here, the W plus channel, so the good channel, and the W minus channel being the bad channel. So let's summarize this. So we basically started from here. Zero, x0, x1, y0, y1, W channel, our physical channel. And we basically translated this now in artificial channel. It's a little bit something in here. Basically, in the first step, y0 and y1, basically as channel outputs to determine my desired bit value, u0. For the second one, y0 and u0 to determine this is like the binary symmetric erasure channel with error probability. So it was this 1 minus p square. Good one here, binary symmetric erasure channel with erasure probability p square. Bad one, red. Actually, that's the good one. This one green. Sorry. So, and the good one. Channel W minus channel. Let me write again related to your comment. So those channels now basically include our pre-coding network. So here, artificial channels. Being explain one thing which might be a bit hard to understand if you look at this first. So about this channel outputs, why do I have U0 now as channel output here? Just start again thinking about the physical channel. So if I look at this first physical channel here, from my observation Y0, I want to estimate X0. This is my task when I think about decoding. How to get from the output the value of the input. And here it's the same. If we look at our first artificial channel, we used Y0 and Y1 to determine the value of U0. Observations, which I refer to as channel outputs that I use, are Y0 and Y1, and I use them to determine 0. For the W plus channel, I consider as channel output Y0, Y1, and U0. So those are the values I have available that I observe, and I use those values to determine the channel input 1. So don't be confused that U0 appears here. It's related to the fact that we use all the three guys to determine. See? So to think about scribe is pre-code. Right. Formal description. Scribe. Pre-coding. By matrix. Basically, I want to find a matrix how to get x0 and x1 from u0 and u1. That's where you can think about this. So this will be the matrix. What I have to multiply my u0 and with in order to get here values x0 and x1, whereas x0 should be u1, u0 plus u1, and x1 should be just the same as u1. Just briefly think about the entries in the matrix, so you should determine this matrix quite easily. Entries in this matrix. first row will be 1, 0, 0. Yes. So see, the answer was correct here. We have u0 times 1 plus u1 times 1. This will go here. Exactly what we wanted. And for the last one, we have u0 times 0 plus u1 times 1. This goes in here. So this way we will get just... we call this the matrix G2. As we will see later on, we extend this somehow further and this matrix will become larger. This is just for the most simple case if we just consider 2 channels. So this was also extend the story. Extending. Example. Let's do it this way. So we have a W minus channel. W plus channel. So now thinking as artificial channels. And now I just want to use another pair of these channels. Assume we just did this twice. Main idea is to apply exactly the same pre-coding again now on our artificial channels. So what I do is I want this guy together with the second W minus channel. Extending the example, using the same idea again. And about our example, we started with binary symmetric erasure channels with error probability 0.1. W minus channels are basically binary symmetric erasure channels with error probability 0.19. And now I combine these 2 worse channels again in the same way. This will result in a worse channel. So the red ones will become worse, the green ones will become better. That's the whole idea of, yes, compound. So this will be the main idea of this channel polarization. Basically, by applying this precoding over and over, we will polarize our channels more and more. So at the end, we will end up with some like almost perfect channels. And on the other side, we will end up with some almost useless channels. So that's the main idea of this channel polarization. So let me also draw this in color. You don't miss the overview. So this is related now to our W minus channels. It's already will result channels. But we do the same for our W plus channel. This basically will result even better channels. This is basically the whole idea, channelization. We will get something for artificial channels. Let me use colors again. So we will get like a W plus plus channel. So the really W minus minus channel. Plus minus and a W plus plus. Again, including this new precoding network now artificial channels. So an example where I have here for an example where P 0.2 should have used the same number EG P, so from the original physical channel will be 0. Get here P minus minus. So for the worst case, 0.5. Get the P plus minus be 0.08. Get the P minus plus 0.1. And we get the P plus plus be 0.0. Okay. So here's the question. What about this W plus minus? Yes, this is basically one of the two channels like resulting from the combination of W minus and W minus. Let's see. It's more clear. So basically, this guy's so from this guy, this guy, these first two guys, and also from combining the two good ones, just a bit resorted. These two resulting channels. We will see this more clear example in but before we look at an actual decoding example, show you this polarization also using my lecture slides. Okay, so here you basically see the same thing that we have drawn here in the lecture, applying the precoding again to our W- and W+ channels, which results in these 4 new channels. Again, precoding included in this new artificial channels. So then, example with the numbers. So we see the first one really bad, very high probability that things go wrong. Last one really, really good. So then we basically extend this idea. Just here. Now, if we are thinking about actually the transmission of this, we would of course use the good channels for our information bits. So using 0 U here as information bits, and the inputs for the bad channel, we would use like the frozen bits, like the redundant bits. So we use the good channels at the end, transmit our information bits, and we use the bad channels just applying some so-called frozen bits, so redundant bits. Yes, yes. Exactly, yes, yes. Yes, yes. Yes, yes. So here one student commented on also on the relationship between the LDPC codes. So in the LDPC codes, we got the improvement by more and more iterations. Here we get the improvement by enlarging this idea using more channels, such that we will get more good channels and more bad channels. And basically how this scales, I've shown you also on, so it should be like the next slide here. Yes, here basically on this slide, you see how things actually will work if we extend this more and more. So for the 4 subchannels, I basically plotted here a histogram of the values that appear. So you see our very good channel with very low error probability appears 1. Then we have 2 like with like 0.1 something. And here we have the really bad one with 0.56 occurrence. So here we already see a kind of separation into good ones and bad ones. If we use 16 subchannels, we will see that we get about 10 subchannels with very low error probability. And well, here 6 with some intermediate errors, or really bad, like the W minus 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 channel here, like there with like an error probability of 0.9. Almost useless. Whatever you put in there, you will get the erasure symbol at down. So this one is somehow useless. Those ones are very good. Extending this further, like 256 subchannels, you see the polarization becomes more and more clear. So you get approximately here like 180 almost perfect channels, and here like 30 like really bad channels. And extending this further like to 1 million subchannels. Actually, I did this on purpose, so extreme. So then you see the polarization is like almost perfect, so nothing in between. You will end up with, like in this case, like 200,000 completely useless channels, and like, or 800,000 almost perfect channels. And actually here you will see the relationship to the channel capacity. So if you calculate the channel capacity for our original binary symmetric erasure channel that is related to this example, you will find out it has a channel capacity of like 0.8. So if I transmit one symbol, I can transmit the amount of 0.8 bit information in it. So, and we actually see this here. If I come up here with 1 million subchannels being perfectly polarized, I will have 800,000 good ones. So if I would transmit now 1 million of bits, I could transmit 800,000 bits like error-free. Transmit 800,000 bits information with. So, and well, the fact that we get here really bad channels is due to the limited channel capacity. Transmit everything completely error-free. If we have a binary symmetric erasure channel with a certain error probability, errors will occur, and that's the extreme case or the asymptotic case. Basically, if we drive the polarization all the way to the end, we will see this perfect polarization in the useful channels and the completely useless channels. Okay, so this is basically how this would scale up. Yes, the fourth case is like the completely perfect distinction between and the band. So no channels in between. And this, of course, would be also used then in this way. Just imagine this one again. Imagine this with our example where we have 1 million channels. We will have 800,000 subchannels with really like almost perfect bit error probabilities. There we would assign our information bits, and we would have like 200,000 subchannels with very high error probabilities. So the useless ones, like error probability 0.99, we would transmit our frozen, our written bits there. But we could transmit 800,000 bits error-free. So this is basically channel polarization. Still, we have one more thing about the. Let's think about this one, unless there are questions related to this polarization. So of course the error probabilities will just up. So you would say, of course, this here is like the error probability P minus. This is the error probability P plus. and then repeating it again, you will get an error probability p plus square for the good channel and an error probability of this guy, or exactly using p minus instead of the p in here will give you the error probability of the next channel. And so this will simply scale up. Ah, okay. So here's the question, why the probabilities don't sum up to 1. Well, it's basically error probabilities on our channels. It's not probabilities of certain outcomes. So of course they don't have to sum up to 1. Just imagine our first example. Of course, also here we have channels with error probability like 0.1, 0.1. There's no relationship that we can say this needs to sum up to 1. So it needs to sum up within our channel model. Yeah, of course, the error probability needs to sum up with the probability of the correct transmission. I just consider several binary symmetric channels. There's no relationship that we can say probability needs to sum up to a certain level. Okay. Yes, yes. Yes, yes. Yes. So let me so here was again the question related to the redundant bits and like the assignment, the redundant bits and the decoding. So this one again. So of course you could wonder why we cannot decode all the bits correctly. Obviously we have some useless ones, but as I said, this is due to the limited channel capacity, so we cannot transmit like with unlimited information rate. This is what strained channel capacity from the noisy underlying channel. So this is why we need to come up with an assignment bits on the good channels and on the bad channels. Not sure if I got the question correctly. Repeat it. Okay. I think now I got the. I think now I got the question. So the question is that we send redundant bits over the useless channels, and we also use this redundant bits for the decoding. And if this is not bad to do it, they will be transmitted wrongly, very likely. So how can we use them in decoding? Yeah, so that's a good question. And we will actually see this when we talk about talk a little bit more about the theory, how to decode these guys. Yes, yes. Basically, in the next step, I want to come up with like equations, how to determine, let's say in this example, our 4 input bits from our 4 observations at the receiver. Think about this. It's not so much time left, but we start already with the first example. So looking at the decoding. And then we might see the problem that you brought up. Where do we use like useless bits in our decoding process? Decoding. So in there, I basically start again by drawing the whole thing with the underlying binary symmetric channels. So with the W, so not the artificial channels, but channel W, the corresponding recoding network. Leave some space to the left, some more. X0, Y0, U0, X1, and well, we need this structure twice. Understand what is going on here. Get some more outputs, Y2. It's the same structure here at the input. X2, X3, U3. Here was then again applying our precoding. These guys. It's here B 0. Guys. Let us have a look. First one, I want to code U0. Say here. It's channel. W minus channel. And I do this simply by coming up with a table. So table Y0, Y1. And what we can conclude on U0. Soon we observe a 1 here and a 1 here. So no erasure event, so correct transmissions on both channels. So this means x0 is a 1 and x1 is a 1. If x1 is a 1, so 1 is going up here. X0 is a 1, so I need to ask what needs to be added with 1 that the result will be 1. 0. Yeah. In this case, we can 0 to be 0. This is observe a 1 here, up 0 here. So 0 plus what is 1 plus 1. 0 here. 0 up here, 1 here. So 1 plus what is 0? 1 plus 1, 0. 0 here. 0 here, 0 here. 0 plus what will be 0? 0 plus 0 will be 0. So then we can also have the cases with the erasure symbol. So let's start with an erasure event on the first one. Say a 0, second one. We don't know y0, so we don't know x0, so we don't know the result of the sum. So there's no way we can determine u0. Of course, the same. 1 here, so no way. What else do we need to consider? Question marks here. So what if we have an erasure symbol on the second one? So we know a 1 here, 0, x0, 1, but we don't know what is here. So if we don't know what's added here, we cannot tell the value of 0. Way we can tell. And also if we have twice the erasure, also no way. So we can finally come up with the decoding function. Let's call it b minus y0 and y1. So those are the inputs. Yeah, well, you could say it's the modulo 2 sum of y0 and y1 here for this first 4 guys, or an XOR. It's described as XOR 0 XOR y0 being not erasure symbol. It's the erasure symbol. And this is basically it today. So next week we will continue there. I think it's straightforward. Feel also free to look at the lecture slides already, because we will also decode the second W minus channel. Then we will think about how to decode the W plus channel and how it goes together. But for today, we are done. Also, for the students in Kazan, have a look at this last page, the decoding of the W minus channel. Maybe this is also interesting for the exam. All right. So then that's it for today. Also for the students in Kazan, if you have questions while you prepare for the exam, feel free to write me emails, so I will help you in any case. Here we have one more question. Any questions are we expected to answer for the exam, and will there be questions? So I think overall we have 10 questions, like 5 from Mike Wolf, 5 from my side. My questions bring a little bit more points, so it's the bigger part. Yes, there will be also a question on polar, but not more difficult as what we did. So then that's it for today. Thank you for your attention. And as I said, for the Kazan students, feel free to write me emails when it comes to questions during the preparation for the exam. Okay, goodbye and have a nice day.